Welcome back, everybody. This video is going to be part 1 of 3 on solving linear equations. Let's get started. A linear equation is a single variable equation, we'll call that variable x for now, that looks like ax plus b equal to 0, where a and b are just some numbers, some constants. A nice property of equations in general is this preservation property, that the same number can be added, subtracted, multiplied, or divided from both sides of an equation without changing its set of solutions. But how does this actually help us to solve linear equations? Well, it lets us isolate our variable. In other words, the goal is to use this property to get our variable all alone on one side of the equation, so that everything on the right side tells us exactly what the variable should be. Let's take a look at how to do that in a really simple example here. Solve 2x plus 5 is equal to 7. Remember, I can use an operation by the same number on both sides of the equation without changing its solution set. First, I notice that I have a plus 5 over here. To get rid of it, I want to use the inverse operation to addition, which happens to be subtraction. So I am going to subtract 5 from both sides. And then what I get is, on the left, these 5s are going to cancel out, and I'll be left with 2x only. On the right side, I can combine like terms, and 7 minus 5 is 2. I only have one more step to go. Notice I've got 2 times x. To undo that multiplication, I want to use its inverse operation, which is division. So instead of multiplying by 2, I'm going to divide by 2 on both sides. Now on the left side, my 2's cancel out, and I'm left with just x. On the right side, I can combine my like terms, and 2 divided by 2 is 1. Notice by isolating x, I can just read off the answer. X equals 1. So x equals 1 would be the solution to this equation. Let's try another one. This time, though, I would like you to try pausing the video and giving it a shot on your own. The solution to this equation is 2. How did I get there? Remember, I want to isolate my variable. The way I do that is by using inverse operations on both sides of the equation. I saw I had a plus 9 on the left side getting in my way, so I subtracted 9 from both sides, and that canceled the 9 on the left side and left me over with negative 6 on the right side. Then I still had a negative 3 times x on the left side, and I wanted to get rid of that negative 3. So I used its inverse operation, division, by negative 3 to get rid of it. And that left me with 2 on the right side. Then, since my variable was isolated, I could just read off the answer. X equals 2. But what happens when I've got x's on both sides of my equation? Well, not much changes here. I still want to isolate x on one side of the equation. So let's see how that changes my solution process here. The very first thing I notice is that neither side of this equation is fully simplified. So let's start there. I can distribute this 2 to get 2x minus 2 plus 3 equals, I can also distribute this negative 3 to get x minus 3x minus 3 on the right-hand side. Now I have some like terms to combine. I've got a negative 2 plus 3 is going to give me 2x plus 1. And on the right-hand side, I've got an x and a negative 3x, which together are going to give me a negative 2x minus 3 on the right-hand side. Now we have a dilemma. I've got x's still on both sides of the equation. What do? I move them all over to one side. How would I do that? Well, I've got a negative 2x over here. And remember how I can use the same operation on both sides of the equation without changing its solution set? Well, let me add the 2x over to the other side. That's going to cancel out my 2x on the right-hand side and leave me with 4x plus 1 equals negative 3. And this is a problem we've already seen how to solve. Go ahead and pause the video here to see if you can finish this one off for me. X equals negative 1 is the final solution to this problem. So as you can see, we first fully simplified both sides, and then we just moved all of the x's to one side before continuing. Try using that same strategy on this problem. Now this one looks a little bit scary because I've got those brackets in there, those square brackets, but really those mean the same thing as parentheses. It's just good form to alternate between them so that it's easier for the reader to see where the different sets of parentheses start and end. The answer that I found was y equals negative 2. And I got that by first distributing that negative 3 here, here, and the 5 here out. That left me with the next line where I combined my like terms, and then I had more distribution to do. Just running through all those order of operations. Then, once all my distribution was done, I had some more like terms to combine, and now I'm left with a problem that looks just like the last one we did. I moved all of my y's over to one side, and then that left me with 29 plus 6y equals 17. I subtracted my 29 over, and it left me with 6y equals negative 12. And then I divided my 6 over, which left me with y equals negative 2 as the final answer. For the record, it doesn't matter what side of the equation you isolate your variable on. You should arrive at the same conclusion. From this video, I hope that you're taking away how to solve linear equations. In the next video, we're going to take a look at equations that may not look linear on face value, but turn out to be. Catch y'all in the next one.